Alright, so today we're going to talk about graphing polynomial functions. This is a two-part section just because there is a lot of information. So be sure that you watch both parts. So first of all, a polynomial. Poly means more than one and nomial means number. So a polynomial is more than one term, okay? So it's in the form a sub n x to the x to the n. This big super long equation here. Basically, we can rewrite polynomials like f of x is equal to 3x to the fourth plus 2x cubed plus x squared minus 4x plus 7. That's a polynomial. So notice how the numbers or the degrees are going down in order. And so all of the numbers in front of the x's, those are your coefficients, and they should be real numbers. The first term, in this case, it would be 3x to the fourth. That's your leading term. The coefficient is called the leading coefficient. So in this case, our leading coefficient would be 3. Okay, so here are some examples. If we have f of x is equal to 4, what's the degree? Well, there's no x value, so the degree is 0. The leading coefficient is 4. F of x is equal to negative 5x plus 1. The degree, well, this is x to the first, so my degree is 1. My leading coefficient is negative 5. F of x is equal to negative 3x to the fourth plus x squared minus 18. So my degree, the highest degree, is a 4. My leading coefficient of that term is negative 3. Last one, negative x cubed minus x squared plus 8x plus 1. Highest degree is a cubed, so it's a 3. My leading coefficient, it's negative, and there is an invisible 1 there, so it would be negative 1. Okay, so let's look at some parent functions. If you remember this from the beginning of the semester, awesome. If not, that's okay, we'll review it. If a function is a constant, that means that we have f of x is equal to some number, and we're just going to call that number c. A constant graph is a horizontal line, okay? That's kind of the parent function. Whatever that number is, that's where that line falls on the y-axis. A linear function is just x to the first, linear means line, and the graph is a straight line with a slope of 1 with a y-intercept of 0. A quadratic, this should be pretty familiar. Parent function is x squared, and a quadratic looks like a u. We call it a parabola. A cubic, this is new. A cubic function is x cubed, and this is what the graph looks like. Kind of looks like a snake almost, okay? A quartic, that is x to the fourth, and it's going to look very similar to the quadratic, except at the vertex there, it's going to be a little bit flatter, okay? Quintic, that is x to the fifth. Oh, not x to the third, but it's going to look like x to the third. And again, at the origin there, it's going to be just a little bit flatter. So if you notice, a quadratic and a quartic look very similar in shape. A cubic and a quintic look very similar in shape. So one thing that you can keep in mind is that an even degree is going to have roughly the same shape as a quadratic. An odd degree is going to have roughly the same shape as a cubic. Okay, so if you can remember what a quadratic and a cubic look like, you should be okay. So now let's talk end behavior. End behavior is what's happening at the very ends of the graph. Is the graph shooting upwards towards infinity? Is it shooting downwards towards negative infinity? So something to keep in mind whenever you're looking at these graphs. To the far right is positive infinity in the x direction. To the far left is negative infinity in the x direction. Way down at the bottom is negative infinity in the y direction, and way up top is positive infinity in the y direction. So let's look at what's happening at the very ends of the graph. So we have this function here, 4x to the fourth plus 6x cubed minus x, and this is what the graph looks like. Our end behavior is as x goes to infinity, what is f of x doing? So as we look this way, where is the graph going? Is it going up or going down? So if I trace the graph to the right, it's shooting upwards towards positive infinity. As x goes to negative infinity, so now we look to the left, trace where is the graph going? It is shooting upwards towards positive infinity. So that's the end behavior, okay? And this is an even function, so it's going to have the same end behavior as like a quadratic, okay? Let's look at the next one. So we have f of x is equal to negative x cubed. So negative x cubed looks like just normal x cubed, except it's flipped over, all right? So again, over here we have positive infinity, negative infinity, and positive infinity. So as x goes to positive infinity, so as we look to the right, where is the graph going? So if you trace it, the graph is shooting downwards towards negative infinity. As x goes to negative infinity, so as we're looking to the left, where is the graph going? If you trace it, it's shooting upwards towards positive infinity. And so this is how you determine end behavior. Now there's a relatively simple way to remember end behavior. It goes in a pattern. So if it's an even degree with a positive leading coefficient, for example, if I have x squared, if you remember what the graph of x squared looks like, it's a parabola. The end behavior is shooting up on both sides. Let's say we had a negative leading coefficient, so I have negative x squared. Well, the negative flips the graph over, and so now the end behavior is going down in both directions. If it's an odd degree with a positive leading coefficient, so take x cubed for example, x cubed looks like a snake, and to the left you are going down, and to the right you are going up. If it's a negative leading coefficient, so let's say negative x cubed, the graph flips over. Okay, so now to the left you're shooting upwards, and to the right you're going down. Okay, so like I said, if you can remember what x squared and x cubed look like, and you know what a negative does to those graphs, it's very easy to determine the end behavior of a function, okay? It is really important that you can picture a graph based on the end behavior and the zeros. It's going to take some time, but that's what we'll learn next.